Hi, this is Lab 3. My name is Stuart Ozer. It's about black holes. So we are given two scenarios. In the first, a planet orbits a black hole of an unknown mass. We're trying to find that mass. And then the second, a spaceship launches from that planet, and we're trying to find an initial velocity so that the ship is able to pass, orbit, and then escape the black hole system. The purpose of this lab is to understand gravitational forces, especially regarding really big objects like black holes. So the physics formulas we use here are m delta v equals force times change in time, being that p equals mv here. We also use that the derivative of momentum is the net force. For the force of gravity, we use the magnitude of the force of gravity, g(mm) over r squared. For the position update, we use final position equals initial position plus the average velocity times time, change in time. And velocity update, we use the final velocity equals the initial velocity plus f net over m times change in time. So what we'll see is on the left here is right here, is part 1. We'll see we get a mass of about 1.24 E34. And then on the left here, we have part 2, and we see that trajectory is very clearly altered. So system and surroundings. In part 1, our system is the planet, and the surroundings is the black hole. And in part 2, our system is the ship, and the surroundings are the black hole and the planet. So let's quickly look at the code here. And so for part 1, if we go down here, so first we see my seed is SOzer6 at georgiatech.edu. And then we go down here a little bit. And we see that the mass of the star as given is 2 times 10 to the 30th. This is the seconds in a day. Moving down, we have that the initial momentum is m times v, and final is the same m times v. And then the change in momentum and velocity is the final minus the initial. And then obviously we put that over delta t, we get dp over dt, which is our derivative, so we set that equal to f net. To find the parallel component, we divide the initial by the magnitude, and then we take the magnitude of the change, divide that by delta t, and that gives us, multiplying those two things gives us the parallel component. Now subtracting that from the net force, we get the perpendicular component, and then the magnitude of f net times the radius squared over g times mass of the star gives you the mass of the black hole. Notice that that's the reverse gravitational formula. Now in the beginning we had a list that captured all of the masses of the black holes, and that's what we're doing here. We're capturing them, and then in the end we add them up, divide by the amount we added up, and then we get our average there, which is 1.24 E34-ish. So we can see that just here. Awesome. So then moving on, let's look at the second part of the lab here. So lab 2, we can see that this is the mass of the black hole that we imported earlier, that we just found. I've upped delta t to 8 so it runs for quicker, and I've upped it to 2 hours so that it runs for the full rotation of the planet, full orbit of the planet. Our initial velocity we found was x is negative 4 e7, and the speed in the y direction is 3.5 e6. This was mainly guess and check, but this seems to work very well. And then these, it's just find the r vector, which would be your planet minus your black hole in this case, or for example, planet minus ship, or ship minus black hole, or ship minus planet. Then you find the normal vector, and then you apply the gravitational formula, and you get your force. And then the net force is the sum of those two forces. And that's the same for both of these here. And then we use the position and velocity update formulas right here to find our new velocity and position for both the planet and the ship. Doing that, we can see that this trajectory is very much altered by this black hole. And you can see why I changed it to 8 here. It goes much faster. And there we go. We can see we definitely escaped the system, and we definitely were affected by that black hole. So now we may go back to thing here. And so this is what we saw. We saw an affected trajectory and a mass of 1.24 E34. So then for the what if and what does it mean questions, for the what does it mean in the observable world, we must measure a finite amount of time to determine rate of change. But we can't calculate exactly the infinitely small amount of time, so we're really looking at an average net force. For the what if with a simple adjustment to initial velocity, we can orbit the black hole. For this, we found -2 E7 and 2 E6 work best, and that looks like this. That's all. Thanks.